How does network bandwidth influence distributed machine learning training? So, overall, high network bandwidth is essential compared to limited bandwidth. Network bandwidth influences the efficiency of the distributed ML training by affecting the speed of the data transfer between nodes in distributed systems. High bandwidth is essential for synchronizing model updates, sharing large data sets, and communication between different parts of the system. Whereas limited bandwidth can cause significant delays, bottlenecks, and inefficiencies in distributed training, leading to longer training times and also potentially higher costs. Concept of model parallelism and data parallelism in the context of hardware limits. So, model parallelism is nothing but dividing model across multiple process or devices, like dividing models across multiple processes and devices, whereas data parallelism involves splitting data set into smaller batches and distributing these batches across multiple processes or devices. So looking into detail, model parallelism involves dividing a model across multiple processors or devices with each process with each processor handling different parts of the model. Very useful for large models that do not fit into the memory of a single device. Model parallelism requires efficient communication between processors to ensure timely synchronization between them. Data parallelism involves splitting data into smaller batches and distributing these batches across multiple processors, with each processor training a copy of the model on its data subset. This is suitable for large data sets that can be processed independently in parallel, requires synchronization of the model updates to maintain consistency across different copies of the final model. Techniques can be used to optimize machine learning model for limited hardware resources. In case of limited hardware resources, techniques are model quantization, model pruning, knowledge distillation, edge computing, hardware acceleration, etc. So model quantization, reducing the precision of the model's weight, activations to decrease memory and computational requirements. Pruning, removing less significant parameters and neurons from the model to reduce its size and complexity. Knowledge distillation, training a smaller model to replicate the behavior of the larger model to achieve similar performance with fewer resources. The training model is similar to student-teacher model. Edge computing, processing the data closer to where it is generated on edge devices to reduce latency and bandwidth usages. Hardware acceleration, utilizing specialized hardwares such as TPUs, tensor processing units, designed for efficient machine learning computations. So these are all the techniques can be implemented when there is a resource constraint or when there are limited hardware resources. All these techniques can be used. How can cloud computing resources mitigate hardware limitations for machine learning? Cloud computing provides scalable and flexible resources for machine learning, allowing users to access high performance CPUs, TPUs, GPUs on demand. It mitigates hardware limitations by offering virtually unlimited storage, memory, and computational power, enabling the training of large complex models without the need for significant upfront investment in the hardware. Cloud platform also offers managed services for machine learning, simplifying deployment, scaling, and management of the models. Challenges associated with training machine learning model on resource constrained hardware. So, in case of resource constrained hardware, what are the challenges with training machine learning models? Longer times due to limited computational power, reduced model complexity to fit within memory processing limits, data handling difficulty in processing large datasets due to limited storage and memory, energy consumption, managing power efficiency to avoid overheating and ensure battery life, especially in mobiles, edge devices.